Bismillahirrahmanirrahim. In this video we will discuss about the polar plots. So a transfer function g of s can be written in terms of g of j omega. So if we replace s with j omega, the transfer function is called sinusoidal transfer function. So that sinusoidal transfer function in general can be represented by this equation, that it can be written in this form. It has the magnitude and this is the phase of that transfer function, sinusoidal transfer function. And it can also be written in real and imaginary part form. So we can write it like that this is equal to x plus jy, where x is the real part and y is the imaginary part. And definitely this x part, real part, and the imaginary part, they will depend upon j omega. That is basically the omega, that is in radian per second. So if we change the frequency, so that will change the real part as well as the imaginary part. So if we take a set of x's in which the x-axis will represent the real part and the y-axis will represent the imaginary part of this transfer function. So if we sketch this, let's suppose x plus and jy, this point, that is this one, in this polar coordinates, on this polar coordinates, so that graph is said to be a polar plot. So we will be taking different values of the omega and we will see that how the real and the imaginary part of the transfer function changes, and then we will sketch the locus, that with the variation of the frequency, how the position of the real and the imaginary part is going to change over the polar coordinates, and that will definitely represent the magnitude and the phase, right? A sinusoidal transfer function have the magnitude g of j omega and phase angle which can be plotted for different values of omega from 0 to infinity on polar coordinate, and that graph is called the polar plot. So plot of the g of j omega and its phase as a function of omega is known as the polar plot. Precisely, locus of all points of g of j omega as omega is varied from 0 to infinity is called the polar plot. Okay, now if the angle is measured from the positive x-axis, it is positive in the counterclockwise direction, and if it is considered in the opposite direction, in the clockwise direction, it will be considered negative. Okay, so let's consider this point in this plane. Here you can see this is the real part of your sinusoidal transfer function and this is the imaginary part of your transfer function. These two axes are representing the real and the imaginary axis. This is the polar coordinate. Why we are going to call it polar? Because we are plotting the real part over here on the x-axis and the imaginary part over the y-axis. Now if we suppose that for one particular value of the frequency, let's suppose that is omega 1, we have this point and our transfer function and this value x1 plus j y1. So this one will be x1 and this portion will be y1. So this will be the magnitude of our transfer function at frequency omega 1, and what that magnitude will be x1 square plus y1 square under root, and this is the phase of our sinusoidal transfer function at frequency omega 1, right? Because our sinusoidal transfer function is represented like that. It has the magnitude, it has the phase, and it can be represented like that, x plus jy. So its magnitude will be x square plus y square under root and its phase will be given as tangent inverse of y by x. So for one particular frequency omega 1, let's suppose that we are at this point. So this is the magnitude x1 square plus y1 square under root and its phase is phi 1. If let's suppose you have another frequency that is omega 2, so at that frequency let's suppose that your sinusoidal transfer function will be having this magnitude, and in terms of polar coordinates this will be, let's suppose, x2 plus j y2. So what is x2? This is x2 and this one is y2. So this is representing the phase, this one, and this is phase theta 2 and this is the magnitude from the origin to that point. So that will be equal to x2 square plus y2 square. So that will be the magnitude. So at that particular frequency at omega 2, your sinusoidal transfer function will be having this phase and the magnitude. Now let's suppose that the frequency is omega 3, then if you sketch the real and imaginary part of your sinusoidal transfer function, this is, let's suppose, x3 and this is y3, so its magnitude will be x3 square plus y3 square under root, and this is the phase, and that phase, let's suppose phi, that is equal to tangent inverse of imaginary part, that is y3, over real part, that is x3. So you will get the phase with the help of this expression. So if you evaluate your transfer function for different frequencies starting from 0 up to infinity, and you sketch a locus of that one, just for the sake of understanding, if we say that it is going to change like this if we change the frequency, so this will be the polar plot of this sinusoidal transfer function. So in order to get the transfer function of the in order to get the polar plot of the transfer function, first of all you will have to determine the sinusoidal transfer function that you will get by replacing s with j omega in the transfer function in S domain, and then you will represent your transfer function g of j omega in real and the imaginary part, and then you will vary the frequency omega, and you will sketch the variation in the real and the imaginary part over the polar plot, over the polar coordinates, taking the real part on this axis and the imaginary part over this axis. And what will be the magnitude? The magnitude will be x square plus y square under root, and the phase will be given by this expression. So when you will vary the frequency from 0 to infinity, and you will sketch the locus of all points when the frequency will vary, that definitely your real and imaginary part will vary, so that locus will be the polar plot. Okay, now let's look at the polar plot of some commonly used transfer function. Let's suppose that we have a pole at the origin, so its transfer function will be 1 by s, and to get the sinusoidal transfer function we are going to replace s with j omega, so we will get this transfer function, and in real and imaginary part it can be written like that. Its real part is 0 and imaginary part is minus 1 by omega. So if we now calculate the magnitude of this one, so magnitude of this sinusoidal transfer function is 1 by omega, and if I calculate the phase will be the tangent inverse of imaginary part divided by the real part, so that will be equal to minus 90 degree. So we can finally write our sinusoidal transfer function like that. This is the magnitude and this is the phase. Now if we take different frequencies, let's suppose frequency is 0 radian per second, its real part will be 0 and imaginary part will be infinite, so its magnitude will be infinite and its phase angle will be minus 90 degree. So let's consider that point. So this row, when the frequency is 0, that is marked somewhere over here, that we have the 0 real part but imaginary part is infinite, so its magnitude is infinite, and its phase with respect to this real axis, that is equal to minus 90 degree, that will remain constant. So now if we increase the frequency, let's suppose 1 radian per second, so we have real part equal to 0 but its imaginary part will be equal to minus 1, so its magnitude is 1. So once the frequency goes to 1, its magnitude becomes 1 but its phase remains minus 90 degree. And let's suppose that when the omega is equal to 10 radian per second, so its magnitude reduces to 0.1, so that you can see over here magnitude is 0.1 when the omega is equal to 10 but phase is still minus 90 degree. Similarly, for the frequency of 100 radian per second, your magnitude is 0.01 and the phase is minus 90 degree, and so on. If you take the infinity frequency in radian per second, so the magnitude is going to become 0, will be approaching to 0, and its phase will be minus 90 degree. So as the frequency will be approaching to infinity starting from 0, so you are moving like this. Finally you will reach to this origin, the magnitude is going to become 0 but its phase is still minus 90 degree. So this is the polar plot of the transfer function when the pole is at the origin. Now let's consider a 0 at the origin, then the transfer function will be like that g of s will be equal to s. So this is the sinusoidal transfer function, and in real and imaginary part it can be written like that. This is the real part, this is the imaginary part, so its magnitude is this one, and the phase can be calculated with the help of this expression, and phase will be equal to 90 degree in this case. So this is our sinusoidal transfer function. Now considering different values of the omega starting from 0 to infinity, the real part will remain 0 but the imaginary part is going to change from 0 to the infinity, right? And because of that, this magnitude that is equal to omega, that will be changing. So magnitude is changing from 0 to infinity, and its phase is always 90°. So now if I sketch it over the polar coordinates, right, so this is 0° point, right, this is minus 90° point, this is minus 180° point, because the angles in this direction will be negative. Okay, so now the phase is always 90° or minus 270° from here, and in this direction plus 90°. So this is the phase. So all the points will lie on the positive imaginary axis, because you can see the imaginary part of the sinusoidal transfer function is positive. So when the frequency is 0, y is 0, so you are sitting somewhere over here, and as the frequency will be increasing, so you will be moving towards infinity along the this positive y-axis or the imaginary axis. So when the frequency is going to become infinity, the magnitude is going to become infinity. So this is the polar plot of your 0, which is sitting at the origin. Now let us look at the polar plot of a pole at the real axis. So the generic transfer function is this one. The pole is at minus 1 by t, right? So its sinusoidal transfer function will be obtained by replacing s with j omega. So this is the sinusoidal transfer function, and if you look at the magnitude of the numerator is 1, and of denominator it will be 1 plus omega square t square. So its magnitude is given by this equation, and its phase will be equal to this one. The phase of this constant is 0°, and the phase of this part can be obtained tangent inverse of imaginary part, that is equal to omega t, divided by the real part, that is equal to 1, so minus tangent inverse of omega t, and it can be written like that. So this is the phase and this is the magnitude of this pole which is at the real axis. And if we rationalize this one by multiplying it with the complex conjugate that you can see over here, 1 minus j omega t, if we multiply with that and divide by that, and if we simplify, we can write it like that, and this can be written as taking this one as the real part and this one as the imaginary part. So we can write down this transfer function in the real and the imaginary part, and here you can see this part is dependent on omega, similarly this part is dependent on omega. So when we will be changing the omega, so the magnitude and the phase of this transfer function will be changing. So let's see its plot by taking different values of the omega. So if we take omega is equal to 0, so its magnitude will become equal to 1. When this is 0, this is going to become 0, and similarly this whole will become 0, because the omega is in the numerator as well as in the denominator. So this and this part is going to become 0, right? So imaginary part is 0, and its magnitude is equal to 1, and its phase at this position will be equal to 1. So that point, if you look at in the form of polar coordinates, right, so at this point you have the real part equal to 1 and the imaginary part is 0. So this is your sinusoidal transfer function at omega equal to 0. So we are at this point, and if you start increasing the frequency, if you take frequency equal to 1 by t, so when you will consider 1 by t over here, omega equal to 1 by 2, so it will be cancelled out and you will be left with 1 by under root 2, right? And the magnitude will be equal to 1 by under root 2, and at this point the phase will be equal to minus 45° if you evaluate this real and the imaginary part. So that is this point, and the frequency of omega t, you are at this point, and at this point the magnitude is minus 45°, and the phase is minus 45°, and the magnitude is 1 by under root 2, and at this point you can find out the value of the real and the imaginary part by placing omega equal to 1 by t over here. So if you place omega equal to 1 by t over here, so 1 by t square, t and t square will be cancelled out, so this will be equal to 1 by 2, and that will be equal to 0.5. so your real part will be equal to 0.5, and similarly you can find out the imaginary part. So you can identify this point, and its magnitude will be equal to 1 by under root 2, and the phase will be equal to minus 45°. So now if you keep on increasing the frequency, so if you take it equal to 10 by t, so you will be somewhere over here, right, and its angle will be approaching to 90°. At exactly speaking, it is at minus 84.28. So as your frequency will be approaching to the infinity, so your magnitude will be approaching to the 0, right, and finally the angle is going to become 90° when the frequency is infinite. So you can sketch the polar plot. It will start from this position, and as you will increase the frequency, it is going to take this path, and finally it is going to end at the 0. So this is starting from 0 degree phase, right? And finally it is minus 90 degrees. So this is the minus 90 degree over here, right? So for one particular point, when the omega is equal to 1 by t, you can see the sketch. This is the magnitude and this is the phase. So along the real axis, the variation will be given by this one, because this is the real part, right? So along this axis, when you will change the omega, it will change accordingly. And along the y-axis, the imaginary axis, when you will change the frequency, you can see its variation over here. So it will be negative because of this one. So this is basically it will be with the negative imaginary part. So the y is this one, definitely it will be the negative one. Okay, so now the transfer function of the pole which is at the real axis makes a semicircle in the polar plot. As you will change the frequency, it is going to traverse a semicircle, and that can be proved because we know that the equation of the circle having the center at A and B is given by this one, where r is the radius, right? So in this, if we observe the center, this, if we want to prove it at it's a semicircle, it must satisfy the equation of this circle having the center at this point, and over here 0.5 plus 0j. So this is the center of this circle. So x sorry, A is equal to 0.5 and the B will be equal to 0, the center of this circle. So x sorry, A is 0.5 and B is 0. So from this circle equation we can write it like that. And if we simplify this one by taking the value of the x and y, what is x? X is this one, and that has been obtained from here. That is basically the real part of this transfer function, okay? And the imaginary part is this one. So taking these values and placing it over here in this equation of the circle, so you have this one as the x and this one as the y. And if you simplify this one, if you go through this simple mathematical steps, so finally you will get equal to 1 by 2. So this equation can be written like that: x minus 1 by 2 plus y square is equal to 1 by under root 2 square. So what is the radius? The radius is 1 by under root 2. So a pole at the real axis which is given by this transfer function will be having this polar plot, and this is going to make a semicircle, right, when the frequency is going to change from omega equal to 0 to omega equal to infinite. So it will make a semicircle, and that we have proved, and its radius will be equal to 1 by under root 2, right? So in the polar plot we consider the frequency from omega equal to 0 to infinity. You can consider the frequency from 0 to you can consider the negative frequencies as well. In that case it will make a circle, because if your frequency is changing from minus infinity and is coming towards 0, so this plot will be like that. In that case your imaginary part will become positive, because you are considering the omega is the negative one, right, in this case. So because of this, this will become positive and you will get the semicircle like that. So that will be a Nyquist plot. In the Nyquist plot we consider the frequency from minus infinity to the infinity, but in the polar plots we consider the frequency from 0 to the infinity. And we see that if we vary the frequency omega, what will be the effect over the position of the transfer function in the polar coordinates, right, over the polar plot. So that information is very useful. In the upcoming videos we will see that how we can use this polar plot to determine the stability and to extract some useful information about the properties of the transfer function. Now we look at the polar plot of a 0 at the real axis. So the transfer function of that 0 is given by this equation, that is 1 plus st. So the position of this 0 will be equal to minus 1 by t. So now the sinusoidal transfer function will be obtained by replacing s with j omega. So if we replace that one, so g of j omega can be written as 1 plus j omega t. So its magnitude is 1 plus omega square plus t square, that is given by this equation, and its phase will be equal to the imaginary part divided by the real part and tangent inverse of that one. So that will be equal to tangent inverse of omega t. So as the frequency will change, its phase will change, its magnitude will also change, because the magnitude is also the function of omega. Okay, so now if we look at the real and imaginary part, so real part is always equal to 1 and the imaginary part is the function of the frequency. So now if we look at the position of this 0 in the S plane, so that is this one, that S is equal to -1/t, so your 0 is at the real axis. Now if we change the frequency from 0 to infinity, let's see how the magnitude is going to change. If the frequency is 0, right, so using this one we will get that magnitude will be equal to 1, and from this expression we will get that our phase is equal to 0. Now if the frequency is equal to 1, so our magnitude will be equal to 1 plus t square, and the phase will be equal to tangent inverse of this frequency is equal to 1, so that will be tangent inverse of t, and so on. If we keep on increasing the frequency, if it becomes infinite, so our magnitude becomes infinite, and the tangent inverse of infinity will be equal to 90 degree, right? So finally our phase will be equal to 90 degrees. So here you can see the polar plot of that one. I have taken the real axis over here, it's the 0 degree point, this is the -90 degree point, this is -180 degree point, and this is -270 degree, or from this side it will be +90 degree point. So here you can see that when the frequency is 0, right, omega is equal to 0, so you are at this point, that is 1 plus 0 j, and as your frequency will be increasing, right, so your phase will be increasing like that. This is the phase point and its magnitude is increasing, but its real part is always be equal to 1. The imaginary part is going to increase. So this is a straight vertical line and going up to infinity at x is equal to 1. The real part is 1, but the imaginary part is increasing, and finally when you will be approaching towards the infinity, your phase will be approaching to the +90 degree. So if at the infinite frequency your phase will be 90 degree, and your phase will be increasing as your frequency will be increasing. So this is the polar plot of the 0 at the real axis. So if I summarize this video, we have discussed the polar plot, what is the meaning of the polar plot, and we have seen the polar plot of a pole at origin, a 0 at origin, a pole at the real axis, and the 0 at the real axis. In the next upcoming videos, we will see that how we can use the polar plots to extract the useful information about the system. That's all from this video. Thank you very much.